wenn du willst, komm kurz runter, von da sieht man es. Alles klar. Na dann, nehmen wir dich mal an. Hello and welcome to Source Code Optimization, with and by Felix von Leitner. Have fun.
Good evening. So this talk will mostly be about C and C++ source code level optimizations, and I will show what they look like in machine code. So I will have assembler listings, and most of them will be for AMD 64, but some of them will be x86. You should have no trouble reading them because the instructions are kind of easy. So I chose them so it's readable. The main thrust of this talk is that many people do unnecessary optimizations on the source code level that make the code less readable because they think that in the end the generated machine code will be faster, and in many cases that's not the case. So I did some tests, and basically I just ran them through the compiler and looked at the code. So I might not have the best examples here, and I encourage you to do the same. So if before you do some great optimization, you should do a small test case and run it through the compiler and look at the generated assembly code. It's fun. So the most important thing I'd like to say is that optimizing is important, even if I'm arguing against most of the optimizations here. Optimizing is important, but in most cases, keeping the code readable is more important. And you should learn what your compiler does for you and then help him do it and not get in the way. And that's the most important optimization you can do. And I'll start off simple. So let's say you want to define some numeric constant, in this case 23, and there are several well-known ways to do that. And it's not always just about readability, it's also about debugging. So this is kind of famous, so it's just a warm-up. So the thing that most people do is they just use hash define. The problem is that the symbol, in this case constant, doesn't actually reach the compiler. So it doesn't show up in the object file and not in the debug symbol, so in the debugger it's not available. So many people still do this because they think it's the fastest. Alternatives that are also well known is to use const int, and this has the advantage that the symbol is visible in the debugger, but it has the disadvantage that it actually allocates this number in the data segment. So we can work around that by using static. I will show the code on the next slide. The next alternative is kind of tricky, but it's also a well-known hack from ancient C times. You can use enum, and in this case, it doesn't use any space and is visible in the debugger, so many people use this. So let's see what actually happens if we do this. And I wrote this little code, and you see I add a different number each time, so the compiler doesn't use common sub-expression elimination. So I want to see if any of these actually generate a load in memory, and you can see the compiler always calculates the sum and puts it in the binary as a constant. So in all of these cases, it doesn't matter actually what you do, you get the same efficient code, and you get no loads. So even in this case, when you say it's a const int, it will allocate memory. If we say static, the compiler can actually remove that. I have some example for that too. But you see, in all cases, the same code is generated. So most of the tips that float around that are, or in optimization books, what you should do to get faster code, don't actually work. So you should always question tips and look at the output of your compiler yourself. By the way, I'm saying compiler, and I usually mean GCC. I'm using GCC on Linux. I also tested the Intel C compiler and the Sun C compiler. Different compilers obviously do different things, but you should use your compiler and not just believe me. So I did most of these tests with GCC and the other two, and in cases where the result is different, I hope I won't forget to notice, so to tell you. So this is another example to show the difference between static and non-static const int. So you see that I have two ints here, 23 and 42, and I have this function that returns the sum of them. So you can see that the compiler, this is the code that's generated. Again, there's no loads for neither of them, but you can see that A, so the non-static one, A actually gets put in the read-only data segment. So this wastes a little memory. The question of using hash define versus some other method also applies to using inline functions. And some people use preprocessor defines to do inline functions. So they say this function is called so often or it does so little that I want to save the call overhead, and they use the hash define macro. For example, the abs function to calculate the absolute value of an integer is usually done in a define or as an inline function because it's so small that the call overhead will dominate it. So this is something that's used often, but if you use hash define, you get the same problem that you get with a hash define for constants. The preprocessor resolves it before the compiler even sees it, so there's no symbols in the debugger, and you can't compile without inlining and set a breakpoint. So if there's a bug in your inline function, there's basically no way really to find it in the debugger. So one thing with inline functions, many people think they have to write the word inline. It's a keyword in GCC, and C99 also has it. I have slides on that. You don't actually need to do that. So, but if you do it in GCC, then you will actually get two copies of the code. You get the inline copy at the place where you use the inline function, where you call it, and you got a separate version in case someone uses the ampersand operator to get the address of the function or calls it from an external module. So unless you use static or extern, you get a useless copy. And that's why GCC doesn't inline per default in -O2, because it will generate more code. But if you use static, then it won't generate more code if you call it just once. So GCC will inline even at O2. So let's test this macros versus inline things on these functions. I wrote the same code basically once as a hash define and once as this inline function. And then I have two functions, foo and bar, and one of them calls the hash define version and one of them calls the other one. And you can see I didn't write inline here, but it still gets inline. And not only that, the generated code is exactly the same. Right? So this happens lots of times. Actually, this code is pretty smart if you can appreciate the niceness of this code. I was surprised to see that all three C compilers generate the exact same code for this. And this is tricky because it doesn't have any comparisons or conditional jumps in it. So this is a jumpless sequence, which is usually people try to do this by hand in C once they reach a certain optimization level, but even that you don't have to do by hand. So this is good because conditional jumps are really tricky to get right in CPUs, and they have a lot of overhead in the CPU to predict the outcome of these branches. And in functions like abs, you usually don't know in which way it will be resolved. So this is a difficult thing, and the compiler knows this and generates good code in both versions. So we see there's really no advantage to using hash define for inline. There's some cases where you still will have to do it. For example, if you use alloc A and return a pointer or want to return a pointer to the alloc A stack structure, but that's so rare that you shouldn't really use that excuse. Inline in general, so I already mentioned it, you don't have to write the word inline to get the compiler to inline your code. The compiler will inline anyway, and if you use inline and the function doesn't inline very well, for example, because it's big and it's called all over the place, then the compiler might even ignore your inline keyword and decide that the code is better if you don't use it. So it doesn't make any sense, it doesn't buy you anything, don't use inline. But do make the helper functions static if you want them inlined. So the downside to inlining is that it destroys code locality. I have some statistic later in the talk about how memory bandwidth is really the dominating issue for optimization these days. So only use inlining when it actually makes sense, and one of the places where it does make sense is for range checks. I have some statistics on that too. So there's some subtle difference between inlining in GCC and C99. So the difference is whether a separate copy of the function is output 2. So if you have a small inline function and you use it once, then GCC, if you just say inline, will output 2 copies of the code. If you use static inline, then no symbol is exported because it's static to this static language. It means only used in this object file. So the function code is only emitted if an address of it is taken, and otherwise it's just inlined. And this is the